Welcome to the third lesson in our Vectors and Geometry unit. Today we're looking at using components of vectors to help us solve problems. Our goal is to be able to determine the horizontal and vertical components of vectors and use them to find the resultant of two or more vectors in the context of problems. So the components of vectors just means that any vector can be broken into the sum of a horizontal and a vertical component. And by broken into, I mean written as the sum of a horizontal and vertical component here. So we'll teach by example here. The first example is a train is traveling at 200 kilometers per hour in a direction of north, 55 degrees east. So we talked about these quadrant bearings in a previous lesson. So that means we're off of north, heading 55 degrees towards the east. So I'm going to draw my vector just like this, and the 55-degree angle is in here. Now, the horizontal and vertical component look like this. If I were to start at my vertex of my angle, if I look at the tail of my vector, I'm going to draw a vector going horizontally across the east line, and it's going to stop when I get underneath the head of the vector I'm actually wanting to represent. Okay, so that's the horizontal component. To that, I could then head directly upwards from there, so a vertical, or the north, and then I'm at the head of my original vector. So the sum, and this is a right angle in here, the sum of those two vectors add up to be that resultant, or the original vector there. So we talk about the red vector that I've drawn being the x component of that vector, the original vector component, and the green vector I've drawn, that would be your y component of our actual vector that we're talking about or working with. I'm having trouble getting my screen to place where it's supposed to be. Component. Okay, so from here we're going to talk about how we can get those values. Now, thankfully, we've already done our unit on trigonometry, so we can just go ahead, and I can't seem to get rid of that little green squiggle I drew on there by accident. We're going to go ahead and actually calculate these horizontal and vertical components. So it says determine the magnitude. Now, if I look at that right angle triangle, I want to find my little inside angle here. So inside, right here, that would be 90 degrees. Take away the 55 on the outside. So that's going to be a 35-degree angle in here, and that makes this opposite and adjacent. So from here, I do know the magnitude of my blue vector. It's 200 kilometers per hour. So I'm going to find how many kilometers per hour each one of these independent components would be equal to. All right, so if I want to find the y component, I would be looking at sine, because that is opposite, and this is hypotenuse. And so we could talk about the sine of 35 degrees would equal the opposite. Now, when we talk about that y component, we sometimes just use a vector y to represent that. So I'm going to use magnitude of vector y divided by the hypotenuse, which is 200. Okay, and then I can multiply the sine of 35 degrees by 200, and that's going to give me the magnitude of vector y. So that's equal to 200 times the sine of 35 degrees, and I apologize, I can't get rid of the squiggle in there. And putting that into the calculator, I get 114.7, roughly, kilometers per hour. Now, as far as direction goes, that's heading north. So I'm going to put the direction with it, and it's no longer just magnitude. That's actually my vector with magnitude and direction there. So I took the magnitude, those absolute value signs, off. To get the x component, I'm going to use x, an x vector for that. I would use the cosine. So the cosine of 35 degrees is going to equal the magnitude of x divided by the hypotenuse, which is the 200. So my magnitude of x is 200 times the cosine of 35 degrees. Put that in the calculator. It's going to pop out a value of 163.8. And because that's heading to the right, that's actually east on my compass. So now I have direction. That is my entire vector, including the direction. So those are my two components for that original vector. Example 2 is talking about Bob pulling a wagon with a force of 450 newtons applied to the handle, which is at a 60-degree angle to the ground. What is the force that tends to pull the wagon forward? So I'm going to simplify my drawing, my diagram here. So there's the ground. Here's my wagon. The handle is making a 60-degree angle with the ground. So there's my 60-degree angle. And the force that is being applied is 450 newtons. So that's our magnitude of that vector. What is the force that tends to pull that wagon forward? So what I'm really looking for is the x component here. I'm looking for like the actual horizontal movement as opposed to the vertical, which would be the y component, which I don't need at all. All right, so based on that, I would take my cos, again, because x would be adjacent, so take the cosine of that angle of 60 degrees. That's going to equal the magnitude of vector x, and that's going to be divided by the hypotenuse, which is 450. So 450 times the cos of 60 degrees will give me the magnitude. 60 degrees gives me the magnitude of vector x. And I can put that into my calculator and I get 225 newtons there. So x is going to be 225 newtons, and if I put a direction with that, it's going to be moving that forward. Okay, I don't actually have northeast, south, and west for this question, so forward is going to suffice. So forward. Just seem to be having trouble getting this cursor to move the way I want it to. Okay, so, and of course I should follow that up with a therefore statement. The force that tends to move the wagon forward and that should have N for newtons. Is 225 newtons forward. All right. All right, looking at this next page here, we've got when adding or subtracting many vectors, it's sometimes easier to work with this if we use the components to make it a little bit easier. If I look at the three vectors here, for example 3, the following forces are applied to an object. What is the resultant of these forces? So I have my object. So let me just draw a little box or an object of some sort. I'm going to actually add in my compass to that. I've got 75 newtons that is going south, but 20 degrees off to the east. So here's one vector, that would be force 1, and this little angle in here is 20 degrees. I also have force 2, which is 120, going north 40 degrees to the east. So this angle in here is 40, and that's actually 120. I should have made that vector quite a bit longer, because it's got to be longer than the 75 vector. And then force 3 is 90 newtons, but it's going south 65 degrees to the east. So south 65 degrees to the east, and it's 90. So there it is there, and this whole angle here is 65 degrees. So lots of angles in there. So if I wanted to find the resultant of these, if I used the method that we had learned in the previous lesson, I would take these vectors, pick them up head to tail, move them around, and join them together. But to work with triangles, what I would need to do is, let's say I treated that force 1 as my first vector, and then force 2 adds head to tail. So it looks like that. So we're now here. I could treat that as its own triangle and work to solve for that resultant. And then to that resultant, I would add on my third vector, which I'll try and do parallel here. So that's the parallel of this one. And then my new resultant, let's see a different color here. New resultant now looks like this. So I would have to break that into a couple triangles. It's totally doable that way. It's just, it does take process, takes a few steps. And for people who have trouble working out what angles would be based on all the different angle property theorems and adding things together and subtracting them, it can be a little bit overwhelming and tricky to do. So what I suggest doing, or what we're going to do, is take each of these vectors and express them as their horizontal and vertical components. And then all we need to do is add them all together. So all the horizontal components get added together and all the vertical components get added together. But to do that, we're going to talk a little bit about the fact that if we're moving to the left, it would be a negative direction. Now, where that's coming from is our xy plane. Here's x, here's y. So our x values to the left are all negative, whereas our x values on the right are positive. Similarly, if we're moving upwards on the y, that's positive, and moving downwards on the y is negative. Now, there's also these things called unit vectors. When we're talking about vectors that lie on the x-axis, it is commonly used as a notation. We use I with a hat. Okay, this is called I hat, and it is the unit vector that represents one unit along the x-axis. So one unit along the x-axis. Along the x, that's supposed to say along the x-axis. Okay, so that's I hat. And when you use this up arrow caret symbol, that represents one unit long. Okay, it's called a unit vector. Unit vector, because it's one, its magnitude is 1. Okay, magnitude is 1 there. Now along the y-axis, if we have a vector heading up the y-axis, we call that j hat. Okay, j hat. And what that means is it's one unit, it's a unit vector, so unit vector, 1 unit long, its magnitude is, along the y-axis. Okay, so how does that help us? Well, we're going to take the whole fact that we have the horizontal and the vertical components and just talk about them in terms of the I and the J. All right, so let's look at force 1. So we're going to go with force 1. Force 1, we knew it was heading 20 degrees here, 20 degrees here. So if I look at its horizontal and vertical components, the x bar, or not x bar, I should say vector x, if I look at that, the angle in here is actually 70 degrees. Okay, so the cosine of 70, our magnitude of this vector was 75 newtons, by the way. The cosine of 70 degrees, oh, darn it, 70 degrees is equal to the magnitude of x divided by the 75. Okay, so that means the magnitude of x is equal to 75 times the cos of 70. Okay, I'm going to leave it at that spot right now. I'm not going to take that to its decimal amount. I'm going to now figure out the y component, and I think I've interchanged my colors. I think before I was using the opposite color for the x and the y. But you guys are smart, you can figure that out. Okay, so our y component, if I do the sine of 70 degrees, we're going to get the y component divided by 75, and I said I don't know whether I said 70 degrees or 75 degrees, I might have mixed that up, but it's the sine of 70 degrees. So our magnitude of y is equal to 75 times the sine of 70 degrees. Okay, so what we do to actually represent that force vector, force 1, it's really going to equal the x component, which the magnitude of it is this, but we're saying that that runs along the x-axis. So what we do is we put the I hat beside it to tell us that's the horizontal component. It's running along the x-axis. Plus, so to that we're adding 75 times the sine of 70 degrees. And that's along the y-axis. It's a j hat. Okay, so what I want you to do is do that for force 2 and force 3, and then in the next video we'll talk about putting those all together.